Okay, welcome to our tutorial. And last time we were looking at Gauss's law, and that's where we continue with. So what you see here is the depiction to help here to understand the implication of Gauss's law. We have here some charge distribution, and we have a control volume which expands over this, which fully covers also this charge distribution. And according to Gauss's law, we have to integrate over the enclosing surface of this control volume over the displacement field or the flux density, and that is equivalent to the charges enclosed in this volume. At the same time, if we work with that space charge density, then we know also that the charge included in this volume is obtained by taking the volume integral over rho that is the total charge included. So we can equate these two sides here. Now, we assume that we have here some charge distribution that varies, but it is spherical symmetrical. And for that, we have also looked at the spherical coordinate system. And if you express our dielectric, if you express our electric flux density, then we can make use here in spherical coordinate to write them like here, this V here. This is basically our, in that situation, this is our electric flux density. It has a radial component, which is dependent on R, theta, and phi. It has a theta component, which is dependent on R, theta, and phi, and it has a phi component. And then you look into that sheet with the how to do the integration of vector fields in the different coordinates, then you see that what we are looking at is a surface integral, that what we have to look up. So that surface integral, that is this differential S, or we usually denote it with a A, and we are in spherical coordinates. That means when you take the differential surface element, you have to consider that for your R component, that turns into an R square and a sine theta that you have to also account for. And if you take a volume integration, then you have to take into consideration that your differential volume element has to account also for that spherical coordinates by putting in not only the dr, d theta, and d phi, but also the factor r square and sine of theta. So then we had assumed that we have distribution which is radially given. I mean, it's basically radially symmetric, spherically symmetric, that is given as rho of r, given with a rho naught minus rho 1 times r over a squared. And that is in the region where r is smaller to a, and this rho 0 and or rho naught and this rho 1, these are both constants. So if you just plot the second part here, that minus rho 1 times r over a squared, that would give you a function that kind of decays like that here, and that the radius a, it just becomes minus rho 1. So introduce that and deduct it here from that row 0. So your distribution looks like that it starts at row 0 for r equal to 0. And as the radio increases, it decays here quadratically till the point where it reaches at the radius a the value row 0 minus row 1. And then they have a jump here, and outside for any r larger than a, it becomes 0. So we want to integrate now, so that maybe we can look here at this spherical coordinate system again. We want to integrate over the enclosing surface. So if you look at our phi component that runs here from 0 to 2 pi, while the theta component runs from 0 to pi, right? Otherwise, if it was running from 0 to 2 pi, you would get twice the surface of that sphere. So you have one variable, the phi, running from 0 to 2 pi, and the theta is running from 0 to pi. You could technically also do that the other way around, but that is not the custom way to do it. So we have, on the one hand, if we take Gauss's law and integrate here over the enclosing surface, we have to perform a surface integral on the left-hand part, and we have to perform a volume integral. This is our space charge density that we have here. There we have to perform volume integral, and that we all have to do in spherical coordinates. So our displacement field has a component potentially in r direction, in theta direction, and in phi direction. However, in this example, you see that the charge density has only a variation in radial direction, and therefore we have a spherical symmetry. And then, as a consequence, we have no flux densities with a theta component. Neither do we have any with a phi component. These are both vanishing. And what we have is displacement field that has a radial component. That makes our life also a bit easier. In consequence, of course, the electric field, which is related to the displacement field via the permittivity, also has only an ER component. So the electric and the displacement field only depend on the radius. And there's only, I mean, these are the R components, and in addition, they only also have a dependence on the radius. Now, our task is to calculate the D field and the E field. So we have that equation again. Now, let's look at the first section here. I mean, the left-hand part of that equation. We denote that here, the 1. And we want to look at that a bit closer. So write that out into its components. That is dr, d theta, and d phi. And we integrate here with the vectorial surface element that is given with a contribution in radial, theta, and in phi. So TR, but the other ones are thankfully vanishing. And if you consider that you have to take a differential line element in either of these directions, sorry, a differential surface element, accounting for all those, then you notice that taking the inner product, only the first one yields a contribution. The dr remains here. And now we integrate over the radial component of the flux density, the electric flux density. And here you have to take into account now that we have spherical coordinates. This is just what we took from here. You see, this is the element that's a contribution for the surface element for our ER component. These two here, we don't have any d theta nor any d phi. They are not entering in our integral. But here we need this r square sine theta that we include. And the theta runs from 0 to pi, and the phi runs from 0 to 2 pi. So now you see that this can be simplified, or that can be integrated. We have, on the one hand side, integration from 0 to pi over sine theta over d theta. That gives us minus cosine theta. The boundaries are 0 and pi. This is a 2. This basically takes care of our integration with respect to theta. And the other part is we have to take care of our integration with respect to phi. That is 2 from 0 to 2 pi, and that is just 2 pi. So that takes care of our phi. So you see, there is no dependence of theta or phi on the electric flux density. That's why it makes it so easy. The integration here over theta, there only occurs a dependence with sine theta, which we exemplarily computed here. And here there's only, with respect to phi, there's only a constant. And dr only has r dependence. And so there's nothing else in that integral. This is why we just have to integrate over these respective quantities. And that gives us here, for that term that contributes with that 2 times 2 pi, that is 4 pi, which this adds to us for our integral. So meaning we have here 4 pi r squared dr. This is the evaluation of 1 here. And now we look at the second side, the right-hand side of our equation that we denote here with 2. And that's the volume integration over rho of r. And what is the situation here? We have for rho of r, when r is smaller a, that is part of the problem given. Remember, this is our charge distribution given. So this is rho naught minus rho 1 r over a squared for r smaller equal to 1. And on the other hand, we have rho of r equals 0 once r is larger than a. So what is the evaluation of this integral inside the sphere? And now why are we doing this? You see, this will lead us to get a relation of how the electric flux density is changing and how it is depending also on the as we can basically compute the electric flux density at the surface of our volume, and we can now vary the size of our control volume and see at various radiuses for this spherical control volume how the D field and therefore also the E field is changing. Now we are inside the sphere. What is our charge here? Q of the volume is integrating over the volume rho of R, and we do a spherical integration. We integrate rho of R, and here we have to take now into consideration that we're doing a volume integration in spherical coordinates. So our differential volume element becomes R square sine of theta dr d theta d phi. I denote this here with a prime to distinguish it as a running variable inside the integral from the boundaries that we will be setting. So we can remove this because it is all aligned with the radius. Sine theta dr prime d theta d phi. And what are the integration boundaries? For the r, we run from 0 to r, from theta from 0 to pi, and for phi from 0 to 2 pi. Now let's insert the charge distribution. Rho 0 minus rho 1 r prime over a squared. And now this we carry along what we have here. That is r prime squared sine theta dr prime d theta d phi. So we had evaluated the integration over sine theta d theta over 0 to pi, and we also have evaluated this part here already in the step above, right here. So again, this will yield 2 times 2 pi. That is a scenario right now we are looking at where we are inside the sphere. That means where we have an R, we have some volume here, and our A is somewhere here. So let's continue evaluating this integral equation, the integral term here. This is 4 pi, and what remains is the integration from 0 to r for rho 0 minus rho 1 r prime over a squared times r prime squared dr. So this is 4 pi 0 to r, and let's multiply that r squared into the bracket, the r prime squared. This is rho 0 times r prime squared. This comes from back here, that is factored in here. And in the second term here, that's minus rho 1, that becomes then minus rho 1 times r prime to the power of 4 divided by a square. Everybody agrees? If you have any objection or question, please stop me immediately. So that is now very doable to integrate that. We get for the first term the rho 0, the r prime squared. When it's integrated, it becomes r prime to the power of 3 over 3. The second term is the rho 1, and we have r to the power of 4, or r prime to the power of 4. Then this becomes r prime to the power of 5 over 5. a square. What we insert is 0 and r, and this is why we basically use this r prime here, because now we insert r as the radius of interest, and we integrate it from 0 to r, and as a running variable in the integral, we renamed the r basically in r prime. And that gives us 4 pi rho 0 r to the power of 3 over 3 here, minus rho 1 r to the power of 5 over 5a square. And this is for the case where r is smaller or equal to a. This is in the first, this is in that region, the result. So what is then the total charge when we move to a radius which is larger than a? Once we reach a, the space charge distribution drops to 0. So at a, at the radius a, we will collect the all the charge inside there, and also if we make our volume any larger, it will not bring in more charges anymore, as the charge distribution has dropped to 0 there. So the charge total is the volume, the charge where the volume, where the radius is a, that gives us a total charge. That means we insert for r now for the radius r, we insert a. So this is our total charge. And there you see we can simplify that a little bit, because that is 4 pi times, sorry, this is not an integral, this is a bracket. This is, there we can cut out the a square in the denominator, and yeah, what remains then is 4 pi, the a3 we can also pull out. Then we get here rho naught over 3 minus rho 1 over 5. So what we would like to have is a displacement field, actually, and this we still don't have. But we have seen that 1, what we denoted 1 with this is left-hand part, right, is equal to the right-hand part. So the left-hand part, that was this 4 pi r squared dr, 4 pi r squared dr, and that is equal. And now let's first assume the scenario where we have r smaller or equal to a. That is basically what we have here. Then we have here 4 pi rho 0 r to the power of 3 over 3 minus rho 1 r to the power of 5 over 5a square. So now it is easy to obtain the electric flux density. You see we have this equation. We just divide through 4 pi r square, and then we obtain the 4 pi in the beginning is dropping, so it remains rho 0 times r over 3 minus rho 1 times r to the power of 3 divided by 5a square. And also, in terms of the vectorial properties, this is of course a vector. It has a dr component. So this is our um, dielectric. Oh, sorry, this is our flux density, our electric flux density. And this is basically here our magnitude as a function of R. And this is the direction. And this is magnitude and direction here. That is for any radius smaller or equal to A. So if we are outside the sphere where there's a charge distribution given, and so R is larger than A, well, the equation is not really any different here. I mean, just some considerations. So you still work with the electric flux density that you integrate over the sphere. And on the other side, you integrate the charge distribution. Let me first rewrite that. That is from phi 0 to 2 pi, theta from 0 to pi, just the R component, adjust for the differential surface element in spherical coordinates that brings in the sine square theta, sorry, R square sine theta, d theta, d phi, and this is 4 pi R square dr, just like before. Our Q is obtained by taking the volume integral over phi R, but the total charge in the sphere is reached at the point where R is equal to A. So this means this is 4 pi 0 to A, R equal A, simply because if you recall, the R and the theta is this behavior that it is at A dropping to 0. So we had the total charge is basically we have computed that here. This is this value here. This is a total charge. So now outside the sphere, we also equate 1 equal to for R larger than A. And there we have again the electric flux integrated over an arbitrary sphere because its radial is 4 pi R square times dr. But the total charge now is 4 pi A to the power of 3. And if you resolve or solve for the R component, you just divide it again by 4 pi R square. That means you have A to the power of 3 remaining here. You have rho 0 over 3 minus rho 1 over 5. And you have 1 over R square. So that is just the what you expect way from some charge which is centered in a spherical coordinate system. You have the decay of the E field and of the D field, which is by magnitude proportional to 1 over R square. So you have your D field being dr times ER unit vector for R larger than A. So two scenarios, or not two scenarios, two regions. And this is either we have here 1/3. Sorry, that is 1 over 5. Rho 1 times A, R to the power of 3 a to the power of 5 for r smaller or equal to 1. And the other one is here, this a to the power of 3 over r squared rho 0 over 3 minus rho 1 over 5. This is for r larger than a. So if you plot that, you get first the kind of linear. Yeah, here's your a. In the far end, you get a decay of the field which is proportional to 1 over r squared. So for r larger than 0, for r0, sorry, for r0, you haven't integrated any charge, so your d field is also vanishing. For small r, you have a dr which is actually proportional to r. For large, see, for small r, this term here will dominate here. And for large r, yet smaller than a, the component of the electric flux density will be proportional to r minus r to the power of 3. Here at the point, here at this point where you, oops, sorry, where r over a is just equal 1, your the magnitude of dr will be a to the power of 3 divided by a to the power of 2. So you will just have this value if you want to plot that. So this value will come here to 1. This is this value here. So what you have to consider here in this equation for r smaller or equal to a, that for very small r to a ratios, you will have this term dominating, and if r over a becomes larger, then this term will be dominating. So you can qualitatively use that to sketch the graph. Higher or larger, make that larger. While if r over a is larger than 1, then the cubic term will be dominant. So the important takeaway also that is that the dielectric flux, the electric flux density depends only on charges. Also, D is continuous. There is no jump in it that you see also in the sketch graph here. But of course, you can plot that function nicely in some plotting tool. While for E, you can have a jump, and you will have a jump if your material changes. That is not continuous usually. And also you see that the D field is decaying with 1 over r squared for large r. That is just similar to the case where you have the field of a point charge, because if you actually zoom out from a very large distance, you have even that charge distribution will amount to nothing else but a point charge. That local charge variation with the radius r is at a large distance, it should not be of significance anymore. So if you go very far out, this is just like a point charge. And so you also have the field dependence like for a point charge. Okay, so this you can use now this relation for from the Gauss law to determine the C field very nicely, but we also have said in the lecture the more general way to find the E field, and here it works quite nice because of the spherical symmetry. But if you are in a more general problem, what you would do is to go about using the Poisson equation. Let's look into a similar problem where we have a perfectly conducting sphere with a radius r. This is, by the way, the tutorial problem 7. This is a perfectly conducting sphere with a radius r, which is centered at the origin. There we have a charge q, which is larger than 0, and it is stored on the sphere here. This is stored on this sphere here. And the space around the sphere is then filled with a homogeneous dielectric. This here is filled with an dielectric with epsilon is equal to epsilon naught times epsilon r. And additionally, then there exists another space charge density, which is given by rho as a function of r, and that exists here in this range where the radius extends from 2r to 3r, and everywhere else it is vanishing. Now we use spherical coordinates to solve the following problems. And first question is, how is the charge distributed over the perfectly conducting sphere? I mean, we have no charge distribution given, but we want to give reason for our answer. How is the charge distributed on that sphere? Anybody? How would you assume it is distributed? There's a certain amount of charge, and it's a perfectly conducting sphere. You know, the previous example, we started going out from 0 and increased our radius of the control sphere more and more, and that we used to determine then the flux density. But in order to do that here again, we want to know, well, we have to know what is the distribution of the charge, and there's nothing really stated explicitly. What could be the distribution of the charge? Is it uniform over the entire volume of the sphere, or is it accumulating in some part of the sphere? What happens if you put charge on a perfect conductor? Where does the charge go? Hmm? Who wants to give a guess? So it gives a charge q, but where will it be? Hmm? Sorry? So your sphere is a large sphere, fairly large, and it's perfectly conducting. And then you put some charges, so I could make some pluses here. Where would I distribute them on the sphere? Would I in the round area, in the surface area? Yeah, it would. They would. Okay, now of course it would be like a cut through it. It is difficult if I have a top view, then I would still have them uniformly distributed, but you have a sphere, and this can be a solid sphere, and it's a perfect conductor, but the charges will try to, they are all of the same flavor, they're all plus or negative. They will try to maximize the distance between them because they are all repelling each other. And in the end, they will accumulate on a very thin surface layer of the sphere. Basically, they will all be there as surface charges. The charges will be only on the surface of the sphere and all around uniformly distributed on the surface. But there will be no charges inside because they will try to maximize the separation amongst each of the charges. So even though we have not given any charge distribution here explicitly, you know that it's a perfect conductor, and the charges that you put there will accumulate on the surface. Why? So due to this electrostatic repulsion, basically we have. So that's the electrostatic force, but because they're all of the same kind, it is repulsive. That is the electrostatic. And also because we have a spherical symmetry. What is the surface charge density? Yeah, so the surface charge density is a total charge on the sphere, and it is all distributed over the surface divided by the area, and the area is just the area of a sphere. That's 4 pi r to the power of 2. Now the question is, what direction has the electric field? So what is the direction? See, this is also more a conceptual question. What is the direction of the electric field? Do you have a ER component? Do you have a E theta component, E phi component? Do you have a mixture of those? What components does your electric field have? All over, and in terms of the direction of the basis vectors, if you have ER, E phi, and E theta. So it is right that it goes in, it is all over because of the symmetry. It goes in all directions, and because of the symmetry also, so it is going in all directions. But that applies to the because of the symmetry only to the ER component. So we have it uniformly in all directions. No, not uniformly, but we have it symmetrically in all directions. And the electric field has an ER component with radial dependence, and the basis vector is ER. And it is independent. Gauss's law. Take the enclosing surface and integrate over the flux density, taking here the differential surface element, is equal to the charge which is enclosed at whatever that control volume is equal to the volume integral over the space charge density over this control volume. So again, this we have just seen. If you integrate in spherical coordinates over D field, you have this 2 integration here for phi from 0 to 2 pi, for theta to 0 to pi, r dr. And there you have this, what you seen as what you need as differential for the differential area element in spherical coordinates for the r component. This is this r square sine theta d theta d phi, and this is just 4 pi r square dr. This is, by the way, valid for all regions, and regions, I mean those here where we are with r smaller than the big R, smaller than 2r, or smaller than 3r, or also larger than 3r. This is valid for all regions. And now we take our first region. The first region is this where r is larger than 0, but it is smaller than the capital R. This is our second region. This is our third region. And this is our fourth region. Yeah, these are our regions. So now we are at region 1. And what is the right-hand side of our Gauss law? What is the total charge? Well, we just said that the charge is actually, so the region, this is R smaller than capital R. We said that the charge on the sphere, on that sphere is actually distributing on the surface of the sphere, That means as long as our R is smaller than capital R, our charge enclosed is 0, because the charge is distributed over the surface of the conductor. Now we have 4. This is on the left-hand side of our Gauss law. We have evaluated the integration is 4 pi r square dr is 0. Well, that still means dr is 0. So d, remember, is our displacement field, or you can also call it, this is our electric flux density. Yeah. Then E is our electric field. And they are related through the permittivity, which is a material parameter. E0 is the permittivity of free space, of vacuum. So as a consequence, because our electric flux density is 0, also our electric field is 0. So both are 0. D is dr, that's the general formulation, times the vectorial component, which is just the one oriented in E direction, and E field is the ER times the vectorial component. But for that particular region, they are both vanishing. Now, region 2, that is where our small r is larger than r, but smaller than 2r. So this is basically the region where you hear, yeah, there is some material in here, but there are no free charges in here. There's no sources to the field. Okay, let's evaluate the Gauss law again. On the left-hand side, we have 4 pi r square times dr. That is always in all regions. And Q of the volume is now just the charge Q that has been added there. So that means in this region, because we have a surface charge on the sphere and all the charge is accumulated over the surface or distributed over the surface, but accumulated at the surface, then the dielectric, in the dielectric material here, we have electric flux density, which is Q over 4 pi r square. This is a function of r, and accordingly our ER, the electric field, is then the dr over epsilon in this material, which is dr over epsilon naught times epsilon r, or whatever we denote it with. That would be then 1 over. So the third region is where r is larger than 2r, but still smaller than 3r. And that becomes now more interesting, because now our charge per volume, so we slowly let our control volume increase. We have an increasingly large radius for our control volume. So what is now captured in our control volume is a charge Q of V again. That is still the charge that has been on the surface of the sphere. This is basically from the metal sphere that is at the boundary of region 1 and 2. There was no contribution to the charge as R became larger than the capital R. So right at capital R, there was a contribution, but then we had no further space charge density in region 2. But now we do have one in region 3. So we have to integrate over our rho over the entire volume. And what is this? So we still carry along our charge q on the sphere. And here, the charge distribution, you see this here, this rho is defined on this ring, extending from 2r to 3r. On that, we have a charge distribution which is alpha over 4 pi small r capital R, yeah? So the small r is the running variable. So we integrate now over alpha 4 pi r prime. I rename this running variable to not confuse it with the boundary of the integral. And we do here now a volume integral. So we have to take our differential volume element according to spherical coordinates. That would be r prime squared sine of theta dr prime d theta d phi. The r runs from where? Well, it runs, the surface charge starts also at 2r, only 2 capital R, and this is the region we are looking at right now, 2r to 3r. So we're starting from 2r to some point that is larger than 2r, that is, we denote with small r. And the theta is going from 0 to pi, and the phi is going from 0 to 2 pi. So that we have already evaluated earlier. So we know q plus 4 pi. This gives us the integration over phi and theta. And what remains here is the integral from 2r to small r over alpha over 4 pi r prime capital R, r prime squared dr prime. And that is q plus, you see that 4 pi actually just canceled out with this 4 pi here. So we only get 2r small r alpha over r. And this here, this r prime in the denominator cancels out with 1 of the r prime squared here. So there remains an r prime here, dr prime. So that is easy to integrate. This is q plus alpha and r are actually not functions of the running variable, so we can also pull them out, alpha over r. And what we integrate is just r prime, and that would be 1/2 r prime squared. And there we enter the integration boundaries. It starts at 2 capital R and it runs to the regular r, the small r. So this is q plus alpha, the 1/2 I also pull out, is over 2r. Then we still have here, we insert r, that would be r squared, and we insert the, as a beginning boundary, minus 2 capital R. And then you have here q plus alpha over 2r, r squared minus 4r capital r squared. Yeah. So then you have this as the right-hand side of your equation, where you equated basically of your Gauss law here. This is what the right-hand side has yielded. This one is this 4 pi r squared dr. So insert both. You have your flux density, the electric flux density in r direction. So this is q divided by 4 pi r squared. This is this part, and then we insert this also. This gives us minus alpha capital R squared over 2r by r small r squared plus alpha over 8pr. Yeah, so here minus 4r squared alpha divided by 2r, and the whole thing divided by 4 pi r. Actually, this one r we can also take out. That you can cancel that out here. And then you get 1 over 4 pi r squared q plus alpha over 2r. Wait a moment. Is there a typo? Let me check. Is this correct? There seems to be something off. In any case, the ER is this there. Wait a moment. This we have to check here. Seems to be a bit odd right now, but I will go back to that in a moment. Let's check the region 4. That is where R is larger than 3R, and there your Q becomes the Q on the sphere, and then we have alpha over 2R, 3R squared minus 4R squared, and that is Q plus 5R. I have to check if this is correct. Yeah. So I think you probably got the concept, and might have to verify that in some quiet moment. We divide that again by the 4 pi r square, and then we get our E field, and that's 1 over epsilon dr. Okay. Maybe it's almost over. Maybe it's good to call it a day now. I'll stop here. We can have a quick look at that again, and maybe complete a bit of it in the next tutorial tomorrow. But also, if you have any questions now, you're still welcome to ask. Well, then, thank you for your attention.
Oh, on Friday we'll have our test, right? Then I'm assuming we will cover up to problem 9, right? Or will we cover until up to problem 8?
Maybe we'll do also 9, but I think I mean, I always say that there may be some there is to some degree also some calculation, but